Hey guys, this video kicks off our series of Chapter 11 topics. So Chapter 11 covers exponential and logarithmic functions, but before we can get into the details of those, we need to refine our rational, technically real exponential concepts. So pretty much everything that you see today is going to be something that you've seen before in Algebra 2. There's only one relatively new concept that I think you'll find pretty simple. So let's go ahead and just discuss some very basic definitions that we know dealing with exponents. So we have four scenarios. If n is equal to 1, then b to the n power, think about this, any number to the first power is just itself. So if n is equal to 1, then b to the n power is equal to b. If n is greater than 1, then b to the n power is, think about something, raising something to the second power, the third power, the fifth power, the 11th power. It's just going to be b times however many times b is. And that's going to be n number of times. And that's just by definition of what an exponent is. Okay, so that's if n is equal to 1 and if n is greater than 1. We also have the scenario of if b is not equal to 0 and n is equal to 0, then b to the 0 power, anything to the 0 power, is 1. Except 0, b can't be 0. Okay, another scenario of b not equaling 0 is that b to the negative n power. So we've dealt with exponents that are equal to 1, exponents that are positive, exponents that are 0. But if we have an exponent that is negative, if we're going to rewrite this as a positive exponent, you simply put it in the denominator of a fraction. So b to the negative n power is the same thing as 1 over b to the positive n power. And I hate to say put it in the denominator because sometimes if you have negative exponents in the denominator, so let me put n aside here. Similarly, if I have 1 over b to the negative n power, in order to make n positive in this regard, then I need to bring this expression up to the numerator to have a positive b to the n. Okay, so it works both ways. Essentially, wherever your negative exponent is, in order to make it positive, you put it in the opposite part of the fraction that it is to start. So here it starts off, in the numerator, technically this is over 1. So to make it positive, you put it in the denominator. Here our negative exponent is starting in the denominator. So to make it positive, I'm going to bring it up to the numerator. Okay, so let's discuss some other properties of exponents. So those were definitions. And now we're going to take what we know about those definitions and review the properties that we know that exponents have. Okay, there are, let's see, 1, 2, 3, 4, 5, 6-ish of them, kind of 5, and then they have an extra. Okay, so we have a product property. And basically it says that if you have two numbers raised to a power, that have the same base. So that's the key, is that if I have a to the m power times a to the n power, so they have to have the same base of a in this case, then that is the same thing as a to the m plus n power. So if you multiply two numbers together, you add their exponents. Okay, we also have the power of a power. And in this scenario, it is exactly what it says it is. You're going to take a to the m power, in parentheses, and raise that expression to the n power. So we have a power n of a power a to the m. In order to simplify this is the same thing as a to the m times n power. You multiply those exponents. We also have a power of a quotient rule, which is similar to this one, except it is going to be a over b to the m power. And what it means is instead of writing it as a fraction raised to one exponent, it's equivalent to a to the m power over b to the m power. So it's almost kind of like that m. I hate to use the word distribution because that's typically dealing with multiplication, but that m applies to both of the numbers on the inside. And of course, in this case, b cannot equal 0 because it's in the denominator and you can't have division by 0. Okay, next we have a power of a product, which is similar to power of a quotient, except we're going to have the product a times b to the m power. And this can be rewritten as a to the m power times b to the m power. And again, it's almost as if this exponent m distributed to both of those terms that are on the inside. Then we have just a regular quotient rule, which is similar to that initial product rule that we talked about, where a to the m power over a to the n power, again, they have to have the same base. This is the same thing as a to the m minus n power. And of course, a cannot equal 0 because then we'd have division by 0. So these are kind of our main properties of exponents. We also have one, there's not really a title for it the way that these other ones have their operations in the titles, but essentially I kind of like to talk about it as, let's just title this exponent with an arrow, both direction arrow in between to radical. And essentially what this is if you have a number, let's say b to the m over n power, this exponent represents the power over the root. So exponents are equal to power over the root. So I can write this into radical form by writing it as, this would be b to the m power under an nth root. So I have the nth root of b to the m, power over root. This is also equivalent to taking the nth root of b and then raising all of that to the m power. So you may not see a difference between these two, but it's just basically the order that you operate in. Do you square the term first and then take the nth root, or do you take the nth root first and then raise it to the, I said square. I should have just said raise to any power m after the fact. And in this case, I do need to specify that the nth root of b must be real. Let's say it must be an element of the real numbers. And of course, that's kind of a given by the title of this section, Real Exponents. So that's it. Those are all the rules. Now, I want to go ahead and make it clear at this point that there's no way that I can do an example of every type of possible scenario that you're going to come across. So I'm going to do a few different examples, 1, 2, 3, 4, 5, 8 of them to be exact, just to kind of give you a good firm foundation of how to use some of these properties. Again, you've used them before. And then after that, it's really going to be up to you to put the properties and the definitions to use in any kind of scenario that I may give you. Okay, so examples. Oh, I can't even spell examples. How about that? All right, so the first part of these examples, the first directions are going to be to simplify. Okay, now when simplifying, and we'll talk about this a little bit later, but basically your final answer should be written as radicals, not with rational exponents. Okay, and additionally, the square root of 16 is not simplified. If you can actually compute something, you need to go ahead and do that. Okay, so when we simplify this, we're going to have the square root of, actually, you know what, before I do this example, or I'll call this example 1, let's say x squared to the 1/2 power. if I ask you to simplify this, basically what the rule is that we have a power to a power, so we can multiply these things. So if I multiply that, then I get x to the 2 times 1/2 is 2 over 2, which is x to the first power, which one would say is just x. Okay, except this is not true for all values of x. And in order to disprove something in math, I can just show one counterexample. So let me suppose, basically what you're saying is x squared to the 1/2 power, basically those exponents just cancel each other out and your answer is whatever's on the inside. Okay, however, if I suppose, or if I take into consideration -5 squared to the 1/2 power, okay, this is claiming, well, actually, let's not claim it, let's actually compute it. -5 squared is the same thing as -5 times -5, which is positive 25. And then 25 to the 1/2 power. 1/2 is another way of asking for the square root. So the square root of 25 is 5. So you see here, our initial value is not the same thing as my answer. Okay, so what you have to be careful about is when variable expressions involve even roots, we need to be careful with the signs. Okay, so for even roots, okay, and that involves denominators of rational exponents. So if the denominator, like in this case, the denominator was 2. If the denominator is 4 or 6, etc. So for even roots, this statement is true. X squared to the 1/2 power is equal to the absolute value of x. And this is true for all x's. So this is the main takeaway that you probably weren't as careful about in Algebra 2. And even when I taught Algebra 2, this was kind of a concept that we didn't really get into. We kind of assumed every time that we were dealing with positive numbers anyway. Well, we're kind of at that level now where we need to be really, really, really specific in our computations and very explicit with what we're trying to say. So I'm going to show you basically what that has to do with your future answers. So here's the deal. I want you to go ahead and simplify the square root of 12 q squared r to the 5th power t to the 7th power u to the 10th power. Okay, so to simplify this, you basically want to break it up into various amounts of terms. Now, some of you may take the square root and put all of your exponents over 2. Like you might want to convert all of your internal terms to rational exponents. That'll be 12 to the 1/2 power, q to the 2 over 2 power, r to the 5 over 2 power, etc. My brain just kind of approaches this problem in such a way that I want to break up all of my terms to be square numbers. Now, if I have a square root, and this goes for square root, this goes for cube root, this goes for 5th root, whatever, this is an important thing to note. Oh, my pen's not writing, which is exactly what I wanted to happen right now in the middle of this video. Okay, there we go. Okay, here's an important piece. An exponent must be a multiple. An exponent must be a multiple of the root for us to be able to take it out of the radical. An exponent must be a multiple of the root for us to be able to take it out of the radical. And in doing so, you simply divide the power divided by the root. And that's kind of what we were talking about earlier in one of our rules. So here's how it works. First of all, let's start with the integer 12. 12 is not a square number. However, one of its square factors is 4. So I can break this up into the square root of 4 times the square root of 3. Q squared is a square number because its exponent 2 is a multiple of the root, which is 2. So I'm going to leave q squared alone because I'll be able to take the square root of it. Now, r to the 5th power is not a square number because 5 is not divisible by 2. However, I can break up r to the 5th power to be r to the 4th power times r, right? Kind of taking my multiplication rule and my product rule and going backwards by breaking 5 up into 4 plus 1. Same thing with t. 7 is odd, so I can't divide it by 2, so I can break up t to the 7th into t to the, go to the even number just below it, which will be 6 times t. U to the 10th power is a square number because 10 is a multiple of 2. So I'm going to leave that one alone. And then what I'm going to do on this next step is actually take the square roots of the numbers that I deem to be square. So the square root of 4 is 2. The square root of q squared is not just q. And again, this goes back to this rule over here. I'm dealing with an even root right now, which means when I take the square root of something, the answer needs to be the absolute value of that number. Okay, now of course I have a positive 2 here because I want to talk about the positive. So I need to put absolute value on that. It's understood. But for q, because I have the square root of q squared, that's where going to be one of those places where I'm going to have an absolute value bar because I want the positive values of that. R to the 4th power is another square number. The square root of r to the 4th power, if I divide power over the root, it'll be 4 over 2, which is 2. So that's r squared. Now, even though that's dealing with a square, or with an even root, any number to the 2nd power, any number squared, is going to be positive because a negative times a negative is still positive. So in that case, that's where you don't need an absolute value symbol. Okay, the square root of r, that's not a square number, so I'm going to skip it. The square root of t to the 6th is going to be t cubed. That is going to be another place where I want to take the absolute value of t and then cube it. Because if it were happened to be negative, then a negative times a negative times a negative could give me a negative number. And again, I can't take square roots of negatives right now because we're dealing with just the real numbers. Square root of t is not a square number, so I'm going to move on to the square root of u to the 10th power is u to the 5th power, right? 10 divided by 2 is 5. And again, I need the absolute value of u to ensure that it is positive, because anything raised to an odd power, I could potentially have a negative number if u were negative. So absolute value of u to the 5th power. So that takes care of all the square terms. And then the other stuff that I couldn't take out of the radical, oh, I took care of 10. All the stuff that you can't take out of the radical just needs to remain inside of the square root symbol. So all of this times the square root of 3rt. So this crazy, ugly thing is our answer. Okay, let's do another example. Again, that kind of practices. The weird part is that absolute value aspect. Again, it deals with even roots, where you're going to have that scenario. I want you to simplify the square root of r to the 7th, s to the 25th, t cubed. So again, you may want to break this up into fractional exponents. I just prefer to kind of do the method that we did in the last question, which is break everything up into square numbers. So r to the 7th is not squared because 7 is odd. So in order for me to take the square root, I need an even term. So I'm going to convert that to r to the 6th times the square root of r. S to the 25th power, even though 25 is a squared number, s to the 25th power is not a square number because it's odd. So I'm going to break that up into the square root of s to the 24th times the square root of s. And then t cubed, same thing. I'm going to break it up to the square root of t squared times the square root of t. Okay, now I'm going to go ahead and actually take my square roots. So the square root of r to the 6th power is going to be r cubed. Again, I'm dealing with an even root. So I have to make sure that my answer is positive. So the square root of r, because if that were negative and I raised it to the 3rd power, it could still be negative. So I need everything to be positive. The square root of s to the 24th power is s to the 12th power. Now, I don't need absolute value bars here, and if that still is kind of like making you question and second guess the reason for them, maybe write this note. Raising s to the 12th power will always, raising s to the 12th power will always result in a positive number. So if it's always going to result in a positive number, then putting an absolute value bar on it is going to be redundant because we know that it's always going to be positive. Okay, the square root of s is not square, so I'm going to skip over to the square root of t squared, which will be the absolute value of t. And then my other three terms, square root of r, s, and t, will just remain under that radical symbol. So there would be my final answer. So those examples really practiced the whole absolute value idea when you're taking, when your root is an even root. Number 4, I want you to simplify c to the 5th power d cubed over c cubed d squared. This is a cube. D squared all to the 1/2 power. So you have choices here. And that's where some of you are going to thrive and some of you are going to kind of spin your wheels and not know what to do because you're going to be afraid to try something. There are probably 3 different steps that you could take to simplify this. Some of you may go ahead and distribute this 1/2 to all of the terms on the inside. Some of you are going to do like I'm going to do, which is take care of our quotient rule first, which is that if I'm dividing terms and they have the same base, I'm going to subtract the exponents. So if I do that, c to the 5th over c cubed, 5 minus 3 is c squared. And then d cubed over d squared is just d. All of that to the 1/2 power. Now, raising something to the 1/2 power is the same thing as taking its square root. So you could rewrite it in that fashion, or you can leave it as it is and think about going ahead and distributing this 1/2 to both of those terms. So then you end up with c to the 2 over 2 power times d to the 1/2 power. Now again, c to the 2 over 2, this is an even root because its denominator is even. So since it is an even root, then c to the 2 over 2 power should be written as the absolute value of c times the square root of d. So if you didn't make note of it earlier when I mentioned this, your final answers should be in radical form with no rational exponents. Unless I specify. So if I give you a number in radical form and I ask you to write it in exponential form, obviously that's a little bit different, but just in general, if you're simplifying an expression, your answer should be in radical form, not with any fractional exponents as a part of your answer. Okay, example number 5. P squared over Q cubed all to the negative 3rd power. So again, you could do a couple of different things. You could take care of that negative power first, or you could go ahead and distribute that negative 3 in to both terms. In doing so, you get P to the negative 6th power over Q to the negative 9th power. And then if you take into account the rule of, okay, when there's a negative, in order to make it positive, you basically flip it to the other part of your fraction. So in order to make P to the 6th positive, I need to bring that to the denominator, and Q to the positive 9th will go in the numerator. So your final answer will be Q to the 9th over P to the 6th. Okay, example number 6. The cubed root of 8x to the 6th y squared. Okay, so you have a couple different options. Some of you may prefer thinking in terms of exponents, so I'm going to do that option, and some of you may just mentally kind of see what should happen. If you think in terms of exponents, remember exponents is equal to power over root. So if I take each of my individual terms, 8x and y, and write them with their power over root, I'd get 8 to the, technically there's a first power there, right? So 8 to the 1/3 power times x to the, its power is 6 over 3 times y to the 12 over 3rd power. Now, 8 to the 1/3 power, you're going to get pretty good at that if you don't know it already. That's the same thing as just the cube root of 8, which we know is 2. And then it's going to be x to the 6/3 power is just going to be x squared. And then y to the 12/3 power is going to be y to the 4th power. Now, we're not dealing with an even radical, so we don't have to worry about any of the absolute value aspects being a part of your answer. Now, some of you could have maybe seen from the get-go that this was the answer. If you just say, okay, I know the cube root of 8 is 2, and then x to the 6th and y to the 12th, you could have just divided each of those exponents by 3 in order to take its cube root. 6 divided by 3 is 12. Like mentally, known that that's what you should have done, is group them that way. Okay, number 7. These last, I lied, I have 9 examples, not 8. For these last 3, evaluate. The directions are going to be a little bit different. I want you to evaluate, which means you're going to have more numbers, and in these cases, I don't think any variables. So for number 7, if I give you 64 to the 2/3 power. So you have a couple different options. You can say, okay, this is the same thing as the cube root of 64 squared. You can say this is 64 squared to the 1/3 power, which is basically the same thing. Or you can rewrite 64 to be, hopefully you know that that's 4 cubed. So if you take, instead of 64, put 4 cubed and write 4 cubed to the 2/3 power. And then did your power rule where you multiply 3 times 2/3. So 3 times 2/3 would be 6/3. And 6 divided by 3 is 2, and 4 squared is 16. Now, I'm very aware that you guys have graphing calculators, and you could simply just plug in your calculator 64, put the little caret to the 2/3 power. I think your calculator understands PEMDAS in this case, but to be safe, anytime I put a fraction in the calculator, I'd make sure to put parentheses around it. Okay, number 8, 27 to the 2/3 power over 27 to the 1/3 power. The rule here is when you divide your numbers, you subtract your exponents. So this is the same thing as 27 to the 2/3 minus 1/3. They already have common denominators, so I don't need to do anything there. I just subtract 2/3 minus 1/3 is 1/3. And again, 27 to the 1/3 power. Power over root. So this is the same thing as the cube root of 27 to the 1st power. The cube root of 27 is 3. If you're not already, you'll get pretty familiar and comfortable with, and hopefully be able to recall very easily square roots, cube roots, 4th roots of your smaller numbers. Okay, last example, number 9. And this is one that we've even done in my class before to an extent already. If I give you something like the square root of 35 times the square root of 10, using our radical rules and our exponent rules, we are allowed to multiply these two terms together. So this is the same thing as the square root of 350. Now, this is not simplified because there are square factors of 350. Hopefully the one that pops out to you is 25. So you can rewrite the square root of 350 times, or is equal to the square root of 25 times the square root of 14. And then the square root of 25 is 5. So this would be simplified as 5 square roots of 14. So again, I want to reiterate, I can't go through one of every type of example that you're going to encounter, but I did one of, a few that I thought were most important. And it's your job to take the properties of exponents, the definitions and the rules of them, and be able to apply that to any given situation.